There's two conditions. Look at sp3, and we'll look at sp2. All right, I'm going to work with carbon alone, no hydrogen. So sp3, I start with a central carbon, sp3 hybridized, and carbon goes everywhere. So each carbon has 4 nearest neighbors, and they're all at 109 degrees, and they all have the same strut length, the same bond length. 1, 2, 3, 4, and so on. Carbon here, carbon up here, and these are going in and out of the board. But I think you can see that one thing is certain: there will be regular arrays in 3 dimensions. Regular arrays. Regular 3D array. And if you look at this from a distance, what you'll find is this is forming the diamond cubic crystal structure. Diamond cubic crystal structure. In this instance, carbon is hybridized sp3. And the consequence of that is diamond cubic. Now, if carbon instead hybridizes as sp2, we know that we have 3 bonds identical lying in the plane. So let's do that one. So here's carbon. Carbon, carbon, carbon. And then this one has 1, 2, and 3 over to here. Okay? And what are we seeing here? We're seeing a hexagonal pattern, aren't we? This is just 3 of the bonds, but I said, look, remember, you got to keep me honest here. Look at this carbon. How many sticks off of the carbon? 1, 2, 3. I told you we better have 4. We better have 4. And I only got 3. So what happened? Where's the last stick? Well, I've taken this configuration over here, all right, S and P, and I've mixed them to get sp2. That means there must be some p orbital here somewhere. And where is it? Well, it's sitting right here. There's a p orbital here, and 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 a p orbital here, and a p orbital here, and so on, and so on, and so on. And it turns out that the bond length is such that these p orbitals are able to bond cooperatively. Okay? And so they form p bonds are cooperative. And they're so cooperative that the electrons are not associated with any particular bond. We say that the electrons are delocalized. And we'll see a little bit more of that later, but you might as well learn it now. They're delocalized. This is the structure of graphite. This is the structure of graphite. And what do we have here? We have strong covalent bonds in the plane, and then we have these weak delocalized bonds normal to the plane. So the planes can slide over one another, which is what gives graphite its lubricity. That's why you squirt graphite powder into a lock in the wintertime to give it some lubrication. So these glide over one another, and furthermore, it's not only lubricity, you get electronic conduction, and graphite has a mildly decent electronic conductivity. Unlike diamond, where all of the electrons are tightly bound, very tightly bound. And by the way, these bonds are very, very strong. The bonds in the plane of graphite are extremely strong. But plane to plane, they glide. Okay, so you can think of these almost diamond-like rafts in terms of the bond strength. But these are flat, and these are 3-dimensional. The other thing that happens is you have really, really tight bonds. What's this optical properties here? This one is transparent to visible light. Why? Because electrons are tightly bound. So you've got this really weak photon, visible light, 2 electron volt photon comes in, and it can't excite anything, but the bonds are so strong that it's refracted. So one of the properties of this is a very high refractive index. Very high refractive index. Whereas here, electronic conduction means it's got very, very low excitation, and hence graphite is an absorber. It appears black because any light that shines on it is absorbed. See, everything comes from the electronic properties. You can explain that it's lubricity, and you can explain its electronic conduction, and you can explain its absorption of photons. Now, I mentioned electronics here and the impact on photonics, you see. High index of refraction, this is socially a very dangerous quantity. Because what happens is, this is what makes diamond so precious. It's not just that it's rare, it's how it functions in society. It takes a small amount of diamond. You know, you're sitting, you're just minding your own business. You just went out, you just want to have a drink, you're sitting there. There's some gal sitting over in the corner of this dimly lit cafe. She's got a diamond stud on. That diamond stud takes a tiny, tiny amount of lumens, and thanks to this insidious property, concentrates them, and then shoots them across, catches your eye, and then the trouble starts. Okay? So this sp3 hybridized carbon is very dangerous owing to this property. Now, I draw your attention to the periodic table. You know, it may happen that some of you are going to feel compelled to make a long-term commitment to another person and initiate that commitment with the presentation of a stone typically made of diamond. Well, I draw your attention to the fact that at room temperature, the stable form of carbon is graphite. Now, I want you to think about this. If you want to present a ring that contains the stone that's symbolic of eternal love, doesn't it make sense to present the stable form, not the metastable form? I mean, I was just thinking about this, but so my point is that this is the stable form. I've done my part to explain it in terms of sp2 hybridization. I leave it up to you to explain it to your sweetheart. Okay, you have a nice day.